series. Geometric sequences in series have common ratios, hence the R. Remember, we're multiplying by the same number over and over and over. Sometimes it's positive, all the signs are the same. Sometimes it's negative, so then they alternate, flip back and forth, which was what was happening here. Sometimes it's a number bigger than 1, so the whole thing keeps growing, and sometimes it's a number less than 1, as in the magnitude. Hence, the terms keep shrinking. Number 8, you guys can see it's a geo. That's a yes. The common ratio is -2/3. Number 14. There's your first 5 terms. All you had to do is plug and chug. Actually, were you plugging and chugging, or were you just doing the pattern? Times 2, times 2, times 2, times 2. Either way, number 24 was also a plug and chug, but this one, once again, was also the pattern. But do you guys remember the name for sequences that are defined like this? Recursive. Good. Recursive. You can't just say, hey, plug in 5. If I plug in 5, I'm finding 6, and I'm using the 5th. You just have to jump, 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 jump. This shows me the pattern of multiplying by 1/3 every time. You wouldn't start at 0 technically because this one gives you a sub 1, so it tells you where to start. Yeah, it tells you where to start. You could start at 0. If it didn't tell you. But recursive almost always gives you your first term. So they could say a sub 0 equals, so you know you're starting there, or a sub 1. At the very end, though, I think you were supposed to set up an a sub n formula. An a sub n formula says, hey, take the first term. There he is, 81. Take the common ratio. Oh, I was multiplying by 1/3 every time. And then plug in the n minus 1. Whoa, whoa. What's going on here? How many of you guys wrote down 243, 1/3 to the n? Anybody? How many of you stopped here instead? Right? So who is this guy? What if we were to take this off to the side? Because they have an equals. They say they're the same thing. So even though that was their final answer, they're saying it's the same as this. How'd they do it? Do you guys remember exponent rules? And how exponent rules say if you subtract exponents, you're actually dividing. It's going backwards of exponent rules. Exponent rules say if you have an x to the a over an x to the b, it's the same thing as an x to the a minus b. So the same way, focus, focus, tricky, 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 tricky. The same way you can go from here to a subtraction in the exponents, you can go from a subtraction in the exponents to the division. And why was that important? Well, I'm not sure if we're getting n. Well, we're kind of getting n by itself. We're getting a term that just has the n, so that's the 1/3 to the n. But what do we do with 81 over 1/3? How do you divide by a fraction? So I can multiply by 3 over 1. I can multiply by 3. That ends up canceling. And what's 81 times 3? Venture a guess? 243. So this is actually a really practical skill of doing exponent rules backwards. Really practical skill of doing exponent rules backwards. This is right, but you wouldn't ever see it fully simplified still looking like this. It'd be like, oh, no, 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 there's a 1/3 in here. There's a division of a 1/3 in here, which is a multiplication of 3, which is a 243. 81 times 3, 243. That was kind of weird, and it was a big old jump. And I didn't know if you guys saw any others of those in homework, so I wanted to show you that even real quick. Number 40, you were just finding your common ratio of 12. Boop, boop. You were plugging in to find the 7th term, which means 6 jumps. It was huge. Hopefully you used your calculator. Number 48, you were taking an nth term. You were asking yourselves, oh, how to make it match. Sorry, Lo siento. Thought it was a lot harder than that. You were trying to make it match. And so there are a few different ways that you could have made it match. You could have started plugging in n is 1, n is 2, n is 3, and seeing if it matched the points that were in the graph. You could have asked yourselves the question, wait, wasn't this section kind of tricky and hard? Did anybody get tricked in on around number 47, number 48? No? It was good? You guys are easy? Feedback would be helpful at this point. How many of you guys would raise a hand and say, I got kind of stuck on, oh, it's not even showing up. Sorry. Nope, it's frozen now. That's even better. How many of you guys said you got kind of stuck on 48? It took you a little while. Yeah, I remember. That's why it was only 3 of you? The rest of you was easy? Okay. I'm still going to peek at it real fast, though, because I thought it was a little tricky. Because if you guys notice, if you started plugging in, if you plugged into every single one of these, all of them start at 18. That one starts at 18, that one starts at 18, this one, even though it's hard to tell, starts at 18, and this one starts at 18. So the hard thing is, all of them started at the exact same place. Now, if you plugged in a second term, maybe it would have been a little bit easier to start distinguishing. However, there were other ways to think about it, and that's what the answer key was trying to tell you when it said over here, as far as its reason or its rationale. They're like, hey, look at the common ratio, and look that he's, well, the series alternates because of the negative, but also 2/3 is less than 1, and they put it in a really awkward way. I would have done absolute value less than positive 1, but either way. Do you guys see how some of these are going down? And some of them are going up? And some of them are bouncing but becoming smaller, and some of them are bouncing but becoming bigger. So if you were looking at these, hold on, the bouncing ones, wouldn't these be the alternating ones? Positive, negative, positive, negative, positive, negative? So both of these are alternating with negative r's. Both of these are not alternating because they're all like positive numbers, whether going up or going down, still all positive, no bouncing. So these are positive r's, those are negative r's. Well, right away, looking down here at the answer choices, I see positive r's right here, and I see negative r's right there. So 48 and 50 had to go to C and D somehow. 47 and 49 had to go to A and B somehow. Now, how do we know the difference between getting smaller or getting bigger? All we have to do is look at less than 1 or greater than 1. Since 47 was less than 1, who is he? Is he A or is he B? A, because 2/3 would make them get smaller. And then that means number 49 is B. And then looking at this one, negative 2/3. What would that be? Getting smaller or getting bigger? Getting smaller. So that's going to be this first one. C must go with 48, and this one's getting bigger. That must be number 50. Anyway, a few different things that you guys should have been thinking through, could have been thinking through to help you out. Number 62, the final answer is 12.5, which, yes, you could have thrown this guy into your graphing calculator. I have shown you how to use the summation button. But, oh, did you guys realize there's a shortcut to summation? You don't just have to do math and then up, 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 up. Remember the shortcut to things is the alpha button? Try alpha y equals. That's where that fraction-y thing is, right? Then try alpha window. Is there anything cool in alpha window? Yeah, see it? Wait, what else is there? Isn't there a lot of things? Yeah. So there are all sorts of different things in there, right? If you guys keep on doing alpha, there's a lot of hidden stuff. You have alpha y equals. You have alpha window. Some of you guys, mine actually only does 1 through 5, which is a little bit sad. But some of you guys, you can keep on scrolling and see more options. I only have 1 through 5, but some of you have more depending on your operating system. Then there's, anyway, you just keep on going all the way down the line. Which one? Oh, what is that one? Is it the factorial, that one?
Yeah.
Yeah, factorial. Yeah. So anyway, there are some cool shortcuts, and I wanted to show you because there's a shortcut to the sigma notation, the summation as well, yeah? Okay. But that wasn't the only way to solve this problem. There was also a way of plugging in the S sub n formula that I already told you was important. Number 78 is one reason we didn't grade homework yesterday, because I was a little worried with the dot, dot, dot. Wait, what's the dot, dot, dot? Why is that different? Infinite, right? Infinite. I wanted to make sure you understood. So question, you see an answer, but why is there an answer? Why isn't it DNE? There's a pattern, but even there are patterns with DNE ones. There was totally a pattern on the one we saw yesterday, wasn't there? Ah, and 2/3 is less than 1. Because this one had a pattern, but it was DNE. It was multiplying by negative 6/5. Yeah. Matthew's over here trying to talk about how this 2/3 is less than 1. So it's a convergent infinite series. Now, some of you might have gotten a little stuck in plugging in the wrong value. You would have had to find the first term, which is found by plugging in 0, which is 9. And you can do 0 power is 1. And then 9 over 1 minus 2/3 is 9 over 1/3. Multiplied by the reciprocal, 9 times 3 is 27. Dun, 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 done. My goodness, her poor little calculator. And homework spiral and whatever else fell over. All right, guys, any questions? Evens or odds? Going once? Yeah.
I needed 79, 81, and 91.
79, 81, 91. Did that get yours, Salma? And then, cool. So let's go ahead and go peek and see what's going on with those weird ones, because we had 3 people be like, ah! Starting with number 79. Oh, it's an infinite one. All right, the infinite one. What's going on? What's the pattern? Times 3? Oh, yeah, totally times 3. I mean, I don't really see it super easily here, but I see it here times 3. Does 1/3 times 3 be 1? 1/9 times 3 be negative? Negative 3, right? So r is equal to negative 3. Why can I, if they're asking for the infinite sum, why can I stop and just say DNE? Yep, if you think about the absolute value, it's bigger than 1, and anything bigger than 1 is going to make it diverge. It, meaning the infinite sum, it's going to get bigger and bigger and bigger and bigger and bigger, and, well, in a really awkward way too, positive, negative, negative. But yeah, DNE because it diverges.
So for infinite, if it's a negative number that's bigger than 1?
If it's a negative number whose absolute value is bigger than 1, then it's DNE. So negative and positive doesn't really make it like converge or diverge. It's more like forget the sign, look at the number. Does that make sense?
So if it's less than 1, then it can be...
Yeah. And then you plug into your formula A1 over 1 minus R. Good. That was 79. Then we had, oh, come on, computer. 79. 81? Oh, that was like the one we did yesterday. How would you guys rewrite this guy? If this helps, like writing it the other way gets confusing. This way, do you guys see how it's 36, 36, 36, 36? But how many decimal places do we need to add every time? Okay, so our common ratio, if we're taking away 2 decimal places, or I should say going to the left 2 decimal places, isn't that not 1/10 but 1/100th? Does that make sense? So I can go ahead and say, yes, it converges because that's less than 1. Then I can go ahead and take my first term, which is 36 hundredths, which is 1 over 100. And then don't we have 36 hundredths? Come on, guys, you're in pre-cal. Who's this? 99 100ths, but then I need to multiply by the reciprocal because I'm dividing. So 100 over 99. Why is this nice? Because it go away. And doesn't 9 go 4 times? And doesn't 9 go 5 times? Dun, 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 dun. Some of you might want to highlight the repeating decimal idea. I'm pretty sure it shows up on a test somewhere. Might be a bonus, might not be a bonus. But if it is a multiple choice, and if you just plug it in your calculator and you try them all until you find the right one, you showed me absolutely nothing about being able to actually do it on your own. You might get the right answer, but you won't get all the points unless you can show it to me this way. Good question, Matthew. There are 2 numbers repeating. So I have to split it up. To make the 36 repeat, it has to be every 2 decimal places. We did like that yesterday. We did like this yesterday. We did like, split this one up. That one's just going to be 1 decimal place, right? But this one, we had to split up. But it was still just adding 1 decimal every time because it was only the 6 that was repeating. The one that we saw, I think, yesterday was it 0.18 repeating? Or 318? No, I didn't just have 1 decimal yesterday. I had 0.3, and then I had 0.018, 0.00018. Check it out, Matthew. It was 1 over 100. This is the one you were asking about yesterday also. It was 2 decimal places, which got you confused. At first, you were confused as to why there was 1. I didn't add 1. I separated. So I saw that that one I split this guy off on his own, and then I split these guys off on their own, and I did a big ol' addition. This is what I was doing for my series, using my formula. Remember, I put parentheses. Oh, that's a times. So I didn't add a decimal. I looked at what I had, and I said, oh, there's my 18, 18, 18, 18, 18. The 3 was in that spot, so I had to start with a 0, but I didn't add the 0. It just needed the 0 for that 3 to work out. I added 2 zeros, 2 zeros, 2 zeros, 2 zeros. And then number 91, is that the last one? Okay. Is that the funny one with the boxes? Okay. I want you guys to take about 2 minutes to talk about in your groups what you thought you were supposed to do on this problem, because it was a tricky one. I think the majority, if not the entire class, is confused. Ready? Pause. I'm going to freeze the screen. Some of you thought about it last night. Some of you skipped it because you're like, should go over it tomorrow because it looks hard. Take a couple seconds to think about, what's the 27 square? Are 27 inches in length? There's actually a new study these days that the more connected you are in social media, who did it? Cambridge? Oxford? I saw it recently. Isolated you are, ironically. And the more depressed you are usually too. It was some huge study that was done at like a psychological one. But anyway, coming back. Danger, danger. The size of a square, 27 inches. So this is 27, right? So couldn't we say the area of this guy would just be, if that's 27 and that's 27, then isn't the area 27 squared? Do you guys agree? Okay, that's easy. But what's going on when you get these ones? I heard you guys say cut into 3s. So each of these squares actually have now a length of 9 and 9. True? Okay. So that means each of them individually, if that's 27 cut into a third and 27 cut into a third, that's 81. And how many 81s do we have? 9. Careful. 8. This is a blank space. So we would have 8 times 81. This one would be 27 squared, right? Then 8 times 81. Okay, what would this one be? You can actually put little commas because they're trying to have you see the sequence, basically. Okay, what's happening here? Oh, my 9s have been cut into thirds, right? So if my 9s have been cut into thirds, then aren't these like little 3x3s? So now instead of having an area of 27 squared, now they had an area of 81, but there were 8 of them. And now we have an area of 9. So each of these, but how many do we have? Well, doesn't each one have 8? And don't we have 8 of the 8? So wouldn't it be 9 times 8 squared, which would be 64? Huh. Can we figure out a pattern? Because I really don't want to think about that one. Do you? Okay, so let's think about the pattern. Very honest. Thank you. I appreciate it. Huh. So first of all, what did you guys get for 27 squared? 29. Okay. But now, like, this was the whole, and now here and here and here and here and here, there's a pattern. So that was the beginning, that was the whole, and then we're trying to compare that, basically. Compared to, okay. I see starting at 81 and then 1 8, and then I see going down to 9 and then 2 8s. What do you guys think the next one would be? Do you guys agree? Yeah. So it's square rooting. Well, wait a minute. Is it square root? Maybe a better way of looking at it, maybe I should have shown this pattern a little differently. Ready? Because wasn't it 9 squared, right? Then it was 3 squared. What would be next? It actually isn't 3. It was a good idea. That is a pattern. It was just not the right pattern. Because 27 was cut into thirds, and then 9 was cut into thirds, and then I need 3 to get cut into thirds. Oh, sorry. I'm going to put it cubed. There you go. That has the pattern. 27 cut into thirds, which meant 9 squared. Then 9 was cut into thirds, so 3 squared. 3 is going to be cut into thirds, so 1 squared. Then 1 is going to be cut into thirds, so 1/3 squared. So kiddos, what do you see here? What happens when you multiply 81 times 8? What'd you get? 640? How about the next one? 576? And then 512? Lauren's subtracting and trying to find another pattern besides the multiplication pattern. Is there a constant subtraction? There's a pattern to it, but it's not constant. So we can't call it arithmetic, and we actually can't call it geometric either, because if you guys notice, like what's being multiplied every time is changing. It's not that you're wrong saying there being a pattern with subtraction. There is a pattern with what's going on, but the pattern as far as what we have, it's not arithmetic or geometric. They were just having you guys kind of think through, can we repeat the pattern that's different and new and beyond what we've already been seeing? So it's called geometry, not because it's geometric. It's called geometry because literally they're talking about shapes. So that's just something for you guys to realize. Three more times. Determine the total area of the shaded. Oh my goodness, sorry, it's not letting me move over here. The center square is shaded. 3 more times. 1, 2, 3 more times. Wouldn't that be 1 more? Shouldn't we go 1 more? Am I wrong? If this process is repeated 3 times, so they cut it and then they shade it, and then 3 more times. 1, 2. I think we only did 2 more times, right? New squares are formed by dividing the original square into 9 squares. The original square into 9 squares, then shading. If this process, no, they're talking about right here, right? Cutting it and then shading. If this process is repeated 3 more times, so I think there's 1 time, there's 2 times, we just need to go 3 times. Okay, so we have 648 goes to that guy, we have 576 goes to that guy, we have 512 goes to that guy. We need to go 1 more time. So guys, what's going to be squared this time? Yeah, the 1 gets cut, and then 8 gets raised to the 4th power. Good. I think that should be your final answer. Sorry, for those of you guys that are checking the odd in the back of the book, I think they meant 1 more time. Even though it's weird because that's 1 beyond the picture, but it'd be really hard to show the next picture anyway. What do you guys get? No, the total shaded area, the area here is different than the area there, right? There's more black space. Do you see it? Because there's more empty space. You're subtracting, subtracting, subtracting from the original. The area you're trying to find is the... Oh, I'm going backwards. I'm going backwards. Sorry. Thanks, Jason. I didn't even read the very last sentence until just now. Shaded region. What was I finding? I was finding the white space. Well, that's easy, though. Guys, we can do the shaded area, because isn't the shaded area just this beginning guy? Take away whatever the white space is. So what's 729 take away 648? 81. Ah. Okay, so that guy take away all the white space is 81. And then you do 729 minus that one, and what do you get?
72.
Wait. That one, take away that one is not 72.
729 minus 560.
I'm guessing 153? The 81 plus the 72. So if you guys want, you could do it that way. Like what Lauren was saying, it'd be 81 plus 72. Then you would go again. Oh, wait, now you're going the other way? You guys are confusing me. Now you're subtracting? Okay. So one more. What's 729 take away this guy? Couldn't you guys just steal him and then put in a 1/3 and have your 729 minus? Come on, guys, get good at your tool. 729 minus 1/3 squared times 8 to the 4th. One line.
It's 273. 273 and then 8 over 9. How do we roll that out?
8/9. You're,
0.8889.
oh, so not 8/9. Oh, you're doing the repeated decimal into a fraction.
Yeah.
Okay, sorry, I thought you were telling me 0.89, but then I thought you said 8/9. I would have done the improper fraction. I wouldn't have done the mixed number, but that's okay. Up to you. All right, cool kids. So let's go ahead and get back to our notes. Binomial theorem. We saw yesterday NCR. We saw yesterday NCR. We saw yesterday NCR. And we have a formula for NCR that you should already have written down in your notes, but I'm going to go ahead and write it up here so we can use it. It all has to do with factorials. We're just going to practice this just a little bit. We practice with factorials because we have to learn how to use it for the binomial theorem. So NCR is pretty important. I highlighted it, or I should say I circled it. We should probably highlight it. It's a pretty important guy because he's the coefficient of a term that allows us to jump to a place in Pascal's triangle. Just reminding you what we're doing. This entire thing is an actual term that we can jump there to get the whole term, but NCR is the coefficient. So yesterday you guys saw me like going. Then I wanted to see if my 70 was correct. I had to figure out what NCR it corresponded to, and then I was able to go ahead and check with the NCR formula as to whether or not it worked, and it totally did. So that NCR, helping us to jump to a particular place in Pascal's triangle. Let's practice. So guys, how would you set up NCR for this one by hand? Oh, didn't you guys just see there's an NCR in your calculator? Okay, that's cool and all. And you need to be able to use it and all, but we have to do it by hand. So let's practice doing it by hand. If I plug in, who goes on top? Good. Who goes on bottom? 8 minus 2, so 6 factorial, 2 factorial. Do you guys notice these will always add up to that guy, if you've done it correctly? This would be 10 factorial over. So this is also an NCR. It's just a different way of writing it. It is actually in your notes. You're not going to see it very often, but if you do, I don't want you to be totally shocked. It does not have a fraction bar. It just has kind of like a little 2-by-1 matrix, sort of. I mean, it's not a matrix. Please don't call it that. But that's what the notation is. There's no fraction bar at all. How about this one? 7C0. 7 minus 0 would be, and then this one would be 8 factorial over 8 minus 8. 8 minus 8 would be 0 factorial times 8 factorial. Now, we do need to simplify. Do you guys see why I would make this one 6 factorial times 7 times 8? Because the 6 factorials can go away, and then I have 1 times 2. Do you guys see how this is just going to end up being 28? Because I can reduce. This one, how would you rewrite the numerator? because we want to get rid of that 7 factorial. And then I have 1 times 2 times 3.
3 cancels with 9.
Yeah, 3 reduces with 9 to be 3.
The 2 can reduce with 8, so it's 4 times 3 plus 10.
120, right? So we're reviewing factorials. Now these ones are going to be kind of iffy. Some of you might be like, DNE, except Joe's saying 1 because we have to remember that 0 factorial is defined to be 1. So in that case, if that's just 1, isn't that just 1? And if that's just 1, isn't Pascal's triangle? Every time you have the highest A and the, well, every time you have the power and the lowest, or you have the power and the highest, you're at one end of Pascal's triangle. So Pascal's triangle, technically, I could say, if I'm raising something to the 0 with power, a plus b to the 0, or to the 1 power, or to the 2 power, or to the 3 power, the r's, NCR, the n is whatever the power is, which is sometimes 0, sometimes 1, sometimes 2, sometimes 3, sometimes 4, sometimes 5. The r is, remember, what the b is being raised to. And remember, that always starts off to the 0 power. So 0 power, first power, 0 power, first power, second power, 0 power, first power, oops, second power, third power. Silly me. I got off one. Anyway, that's why I'm allowed to jump to a certain place like I did yesterday with that 70. Because that 70, I was thinking about, okay, how do I get to that 70? Well, he's in the 8th row. So I know he's going to be 8, and then he's over 0, 1, 2, 3, 4. He's in the 4th spot. That's how I was able to get to that 70 yesterday. Because I was like, okay, what's going to happen to get to that 70? And I figured out he was 8C4. So without having to build Pascal's triangle and add and add and add and add, I was able to jump right here and say, oh, that's 70. Or check it with my factorial formula to be 70. So on top, it's the power that you're being, or the binomial is being raised to, and on bottom it's the position of the b. The r is the power of the b, starting with 0 and building to the very highest. And do you guys notice that? Depending on, depending on what you have, whenever you have a C0 or a C, whenever r is 0 or r is the number that you have, you're always going to get 1s. You're always going to get 1s, and you're always going to get 1s. Everything else on the inside is going to change. So, you guys, don't worry, you don't have to write this down, but this is Pascal's triangle that we've already been talking about quite a bit. So if I was to ask you something like this, let's get real and let's get some real examples in. I don't just give you an a plus b, I give you an x plus 1. We're making it real. 1. You write this out and say, all right, it's time to do a lot of foiling.
No.
You could, but that's not what we're going to do. Instead, we're going to say, you know what, hold on, we know something about 3. We know in Pascal's triangle, 1, 3, 3, 1 is a thing. Whether you were to use something like 3C0, 3C1, 3C2, 3C3 to get there, or whether you would just do your Pascal's triangle like we've done multiple times over the last couple days, and you would just end up at 1, 3, 3, 1. Either way, you get there. But that's not the end, that's just the beginning, because what else do we still have to do? According to the binomial theorem, a needs to be raised to the, where does a start? A is the x. He's going to start at the highest, and what's going to happen every time? It decreases until he's to the 0th and he's gone. A starts at the highest and counts down. That's what binomial theorem tells me when I'm expanding a binomial. That first guy starts at the highest power and counts down, counts down, counts down, counts down until poof, he's gone. Who starts at poof, he's gone? The second guy. Y doesn't start at 9. Y starts, remember, these have to add up to, their powers have to add up to n every time. So if this guy has all the powers, well then Y has nothing. But then all of a sudden Y has 1, Y has 2, Y has 3, all the way up until Y has n. So as X is counting down, in this example, who's counting up? Well, hold on. Who starts off really not being there at all? The 1, the second guy. But then he ends up coming into the 1 and then coming into the 2 and then coming into the 3. Now, in this example, though, did that really make that much of a difference? Because it was a 1. But what if it was a 2 or a 3 or a 4y squared? It would make a big difference. So at the end of the day, I have x cubed plus 3x squared plus 3x. Just plugging into binomial theorem, not having to do any of that multiplication. But guys, it gets harder than that. So, it gets harder than that. So, I have 3 pieces to every expansion of a binomial. What are the numbers in front, the coefficients? What are the powers of the first term and the powers of the second term? Can anybody look at the Pascal's triangle we did yesterday? Anybody do it with me? Do you have the row for 5? It's 1, 5, 10. No. 1, 4 would be to the 4th power.
Oh, yeah, you're right.
1, 5. Do you guys double check me? Is it 1, 5? Well, hold on. We're supposed to have 6 terms. So 1, 2, 3, 4, 5, 6. Good. Okay, I got there. Who starts off being raised to the 5th power? The first guy. So who's the first guy? 3a. What's going to happen at 3a every time? It decreases until poof, he's gone. And now poof, he's gone, right? Okay. But as 3a counts down, question, who counts up?
The negative 4b.
Ah, because I need to make this an addition of a negative, so careful. So I'm going to have a negative 4b. Oh, wait, doesn't he start off to the 0, though? Oh. Okay, then let's just, there we go. He starts off to the 0, but then he starts appearing. Negative 4b to the 1, then negative 4b squared, then negative 4b cubed, then negative 4b to the 1, 1, 2, 3, 4, and then negative 4b to the 5th. Now here's the crazy thing, guys. Do you have Pascal's triangle in here with the 1, 5, 10, 10, 5, 1? Yes. But when you plug and chug each of these into your calculator, you're going to get an a to the 5th, but it's not going to be 1 a to the 5th. Isn't it going to be 3 to the 5th, a to the 5th? So if you have 3 to the 5th, because you actually have to raise that 3 to the 5th also, the 1 was important, but you're going to end up with 243 a to the 5th. And actually, the next one's not even going to be a plus. Why is the next one going to be a minus? When you do 5 times 3 to the 4th times negative 4, it's going to be a negative number, negative 620, a to the 4th b. Now, was the 5 important? Yeah, he had to get multiplied by 3 to the 4th and negative 4, but at the end, you're not going to see him. He's in there, but he's going to be hard to see. Then you're going to do 10 times 3 to the power of 3 times negative 4 squared, which would be times 16, right? Do you guys see how binomial theorem, oh, the next one's going to be a minus. I'm going to put a dot, dot, dot at that point, because if you're able to get those values, you should be fine finishing it. It is a to the 5th, a to the 4th, a cubed, a squared. It is b to the 0, b to the 1, b to the 2. But with these numbers come bigger coefficients, because they get raised to the powers also. And so they have to be accounted for when you solve. Do you see how, though, I'm still doing binomial theorem? I'm starting with Pascal's. And if Pascal's, remember, if Pascal's ever gets way too nasty, like it's like the 20th, remember, we can jump to where we want to go with the NCR. You don't have to do Pascal's to the 20th row. That would be, that'd be nasty. But binomial theorem, the pattern stays the same. The first gets raised to the highest, counts down, while the second gets raised to the 0th and counts up. So the only thing that we didn't get to specifically practice is what do we do if they say, find me that term? Do you have to do the whole thing to find it? Maybe. Or you just think of, what if I was to jump there? Is there a way? I want you guys to try homework as much as possible. I'm going to put a quick comment in your Google Classroom as far as how far I want you to go. I am going to be gone tomorrow, so we're going to grade this homework on Monday. And you are going to be with a sub. You're going to be watching a couple of videos, maybe some doing extra examples of this, but then the rest, maybe just having fun with things like geometry.